what we saw in the last session, and then today we're going to spend most of our time talking about Büchi objectives. So here's like a very short summary of everything that we saw. First of all, we defined graph games, and then we said that an arena is basically a graph where the vertices are divided into two sets, the set of vertices controlled by player 1 and the set of vertices controlled by player 2. This was, of course, a partitioning, so every vertex has just one owner. And then we also said that because we want the play to go on forever, we're going to assume that every vertex has at least one outgoing edge. And this is an assumption that is quite important for this session. And we talked about how a play of the game works. Basically, we have a starting vertex, and at each time, whenever we are at a particular vertex, the owner of that vertex, the player that owns that vertex, is to choose which of the outgoing edges to take. And then they play this forever. They just keep playing for eternity, and then we will have an infinite path on our graph, and this was called a play or an outcome of the game. Okay. So let me see. So we talked about outcomes. We then defined objectives. We said that an objective for a player is basically a set of infinite paths. And the idea was that player I wants the outcome of the game to be in OI. And then we defined the notion of zero sum. A game is zero sum if the objective of one player is the complement of the objective of the other player. So it means that whenever someone gives you a play of the game or an outcome of the game, you can tell whether player 1 has won or player 2. Of course, this outcome is, again, an infinite path on the graph. And then we defined some classical objectives. So just to refresh your memory on this, reach of T is that the player wants to reach at least one of the vertices in T. So the player wants to see T at least once. Safe T means that the player wants to stay in T and never leave it. Büchi T means that the player wants to visit the vertices in T infinitely many times or infinitely often. Co-Büchi T was the dual of Büchi. And basically it meant that we want to make sure that at some point we enter T and then we remain in T forever. So we want to make sure that the vertices outside of T are seen only a finite number of times. That was co-Büchi. And then we also had parity, which was a much more complicated condition. The idea was that we are assigning a number, a priority to every vertex. And then we're looking at the priorities of the vertices that have been seen infinitely many times. And then we want the minimum among all these priorities to be even. And another thing that I proved to you last time is that Büchi and co-Büchi are special cases of parity. So we will care about parity more than everything else. And then we talked about the notion of strategies. We said that a strategy is basically a function that takes the history of the game and the current vertex and tells you where to go from the current vertex. So it's just a recipe for extending the game. And again, we always use this subscripts to show which player the strategy or the objective or anything else belongs to. So sigma I would be a strategy for player I. And so sigma I only tells you where to go when you're currently in VI, in a vertex that belongs to the player I. Okay. And then we talked about memoryless strategies. We said that the strategy is memoryless if it only depends on the current state of the game and doesn't depend on the history of the game. And then I said something that was wrong. I told you that chess has memoryless strategies. Apparently it doesn't, because there is this rule that if you're in the same state 3 times, you have a draw. So you have to remember some of the previous states in chess. So it doesn't have memoryless strategies, but we can say that, I don't know, tic-tac-toe has memoryless strategies. So again, the whole idea in a memoryless strategy is that you don't need to remember how the game got to the current state. All you need to know is what is the current state, and based on that, you can choose what to do. That's called a memoryless strategy. Okay. We also talked about the fact that if I fix a strategy for each of the players and I initial state, I will have a unique outcome. And we show it like this. That's outcome of V sigma 1, sigma 2. Here, V is the initial state. Sigma 1 is the strategy of player 1, and sigma 2 is the strategy of player 2. And then we said that sigma 1 is a winning strategy for player 1, of course, given some starting vertex V. If whenever player 1 plays sigma 1, no matter what player 2 plays, every sigma 2, the outcome of the game is in the objective of player 1. So it's a winning strategy if you can win no matter what your opponent does. Okay. And then we said that the winning set of a player, so for example, win 1 of O1, is the set of all states from which player 1 can win according to their own objective O1. And by can win, I just mean that they have a winning strategy. Okay. So win I of O, set of all states from which player I has a winning strategy. And then we had this nice definition, which was also the source of several of the emails that I got, but I'm not going to give you the answer to the homework. So we said that a game is determined if from each one of the vertices, exactly one of the two players has a winning strategy, right? So if the win set of player 1 based on the objective of player 1 is the complement of the win set of player 2 based on the objective of player 2. So that's how we define determinacy, and basically a game is determined if from any starting vertex, only one of the players has a winning strategy. Okay, and I have to be very specific about this. So from every initial state, we want exactly one of the players to have a winning strategy. You might have a case where the objective of both players is just the set of all paths and then everyone always wins. We're not looking at those kinds of games. When we're talking about determined games, it means that from every vertex, exactly one of them have a winning strategy. So I also don't accept the case where both of them have winning strategies. Okay, this is going to be part of your homework. Make sure the recording is working. Okay. Yeah, so I haven't released the first homework yet, and the first homework is going to have some proofs in Coq, but this is also part of the homework. So I want you to really think about the difference between zero-sum games and determined games. So let's go back to the definitions here. Remember that a game is zero-sum if the objective of player 2 is the complement of the objective of player 1. And it's determined if the win set of player 2 is the complement of the win set of player 1. Two different notions. And basically, we can have 4 cases, right? Based on whether a game is determined or not and zero-sum or not. So for each of these 4 cases, I want you to either give me a game that is in that case, or prove that it's impossible. So for each of these, you have to give me a game, like a game that is determined and zero-sum, not determined but zero-sum, determined but not zero-sum, and finally not determined and not zero-sum. And if you think one of these cases is impossible, you have to, of course, give a proof that it's impossible. And when I ask for a game, I basically mean that you have to give me the graph. You have to tell me how the vertices are going to be partitioned between player 1 and player 2 vertices, and you have to also give me the objectives of the players. Okay. So this is going to be part of your first homework. But let's go back to what we saw for reachability. Today, I don't want to put too much emphasis on reachability. Today is all about Büchi. But again, I got a ton of emails, so it really seemed like many people didn't understand my reachability lecture, so I'm going to do parts of it again. So this was the idea. Let's say that the objective of player 1 is to reach a particular set T. and I'm showing T here at the center. So what we did was that we did an attractor computation. And the idea was that the attractor of T is basically the set of all states from which player one can ensure that the game will eventually reach T. Okay. And the way we defined this was that we said we can just find larger and larger attractors recursively. So I said that A0 is just going to be T. And so the idea is that if I'm in A0, if I'm in T, I have already won, because my as player one, my objective was to reach T. And if I'm starting in T, the objective is already reached, right? And then I said, okay, let's say that I know that I'm winning in A0. Let's take vertices that are outside of A0, okay? And let's say player one is the red player here and player two is the black player, okay? So here's a red vertex that is outside of the winning set, but it has an edge to it. So if the game starts here, player one can just take this edge and win, right? So any vertex that is like this, any vertex that has an edge to the winning set of player one and also belongs to player one should itself be in the winning set of player one. Because I can just start here, I can just go to another vertex where I win. And then the opposite case was that consider this vertex, this one belongs to player two. But it has only one outgoing edge, and the only outgoing edge is reaching the target. So no matter what player two does from this point, player one is going to win, right? And the same thing happens, for example, here. This is a player two vertex. It has two outgoing edges, but both of them reach the target immediately. So no matter what player two does from this point, player one is going to win, okay? So this is how I defined this second set, A1. So A0 was where player one could win in just 0 steps. A1 is the set of states where player one can win in 1 step, basically. So it's everything that was in A0 union with all the player one vertices where player one can go to A0 in 1 step. Union with all the player two vertices where no matter what player two does, we will end up in A0 in 1 step. And then we said that, well, we can inductively make our sets larger and larger. So if at some point I have a set AN, and I know that whenever the game is in AN, player one is going to win, right? I can make the same argument. I can say that if there is a vertex outside of AN that is under the control of player one, but then in 1 step, player one can go to AN, then, well, player one is going to win. And the same thing for a vertex that be 2, but player 2 has no choice but to go to the winning set of player 1. Again, player 1 is going to win from that vertex too. It's just going to take 1 more step. Okay. So our idea was that we just set A to be the union of all these AI. So I'm just going to create all these sets AI, and then A is the union of all of them. And then we said that, well, I know that for each vertex that was in one of the AIs, one could win. So of course, from anywhere in A, by definition, player 1 can win, because any point that is in A is in one of the AIs, right? But the part that was interesting was that we said, okay, let's say that B is V minus A. So let's take all the vertices that were not in any of the AIs. So in this case, I have these 4 vertices. And I claim that from these vertices, player 2 can ensure that we will never reach T. So if player 2's objective is to avoid T at all costs, there is a winning strategy for that. Now, why is that? So we had this notion of a trap, and we said that this set B is a trap for player 1, which means that player 2 can ensure that the game remains in this set B and never enters A. Okay, why is that again? So consider a vertex in this set B. Okay, it's either a player 1 vertex or a player 2 vertex. If it's a player 1 vertex, it does not have an edge to A. So for example, consider this one. This is a player 1 vertex. It doesn't have any edge to A. Why is that? Because if it had an edge to A, by definition, I would have added it to A, right? On the other hand, if you take a player 2 vertex, let's say this player 2 vertex, it might have an edge to A, but it definitely has at least one edge that doesn't go to. Again, this is based on the definition, because if all of its edges were going into A, I would have added this vertex to A too. Okay. So now if the game is in B, if we are outside of this large circle A, here's a very simple strategy for player 2. Don't ever enter A. Right? So if the game is in B, we know that player 1 cannot take it to A. No matter what player 1 does, the game is going to. And then if the game is in B and you're player 2 and you have to play now, you always have the option of taking a successor that is in B and not in A. And if you just do that, you ensure that you will never reach A. Right? And of course, since the target set T or A0 was a subset of A, if I never reach A, I'm never going to reach the target. So this shows that basically we have determinacy, right? And this was the question I want to ask, but yeah, the game is determined because basically the win set of player 1 with the objective of reaching T is the set A, and the win set of player 2 with the objective of being safe in V minus T, which means never reaching T, is B, and they're complements. So it's determined. And yeah, it's also zero sum. So I solved 1/4 of the homework for you. Okay. But what's more interesting here is that both players have a memoryless strategy, right, in their own winning sets. So what is the winning strategy for player 1 if we are in A? The winning strategy is just go closer to the core. Right, every time if you are player 1 and let's say, I don't know, okay, let's say we're here, this is a player 1 vertex and it's like in A2, try to go to A1 or try to go somewhere closer, and that's it. That's the winning strategy for player 1. And of course, we know that such an edge exists. So for every one of the vertices, I can just pick one of the outgoing edges and I can say, this is what you do as player 1 if you're at this particular vertex. So again, it's memoryless because you don't have to think about how you got here. You just know you are in this vertex, you're going to take this edge, the edge that is taking you closer to them. Okay, that was the strategy for player 1, and the strategy for player 2 is of course what I explained to you, like always remain in B. So for every player 2 vertex that is in B, you just take one of the edges that is also going to remain in B and you just fix that. And that's going to be the strategy for player 2. So player 2 knows that whenever the game, he has to take this one. And again, it doesn't depend on the history of the game. It doesn't matter how we got here. The strategy just says that if you are here, go to this successor. So it's memoryless. It doesn't depend on the history at all. Okay. Now, another thing that was apparently confusing is that I said the runtime is linear, and it wasn't clear how, because, well, we're computing all these different sets. So I'm going to just give you a pseudocode of the algorithm so that I can really prove to you that this is a linear time algorithm. Now, the important point here is that I don't really care about computing A0, A1 to AN. I needed them to, again, mathematically reason about the set A, but what I actually care about is to compute this set, the player 1, which is A. So I don't need to compute all of these. And I can compute A in linear time. So here's how I would do it. So first of all, I'm going to start with my set A being just the empty set, okay? And every time, whenever I figure out that a vertex is in A, I add it to a queue. And the other thing that I do is that for every vertex, I always keep track of how many of its successors are already in A. Okay? So what I'm doing is actually very similar to a BFS here, except that I just have this counter, which basically for each one of the vertices, it tells me how many successors does this vertex have in A. And initially, it's initialized to 0 for every vertex. Okay? So I have a queue, and this is the queue of all the vertices that I should add to my set A. And initially in this queue, I just have all the vertices in T. And initially my set A, which is going to be the winning set of player 1, is the empty set. Now here's what I do. I say, as long as my queue is not empty, let's take one of the vertices in the queue and let's add it to A. Okay? So I choose a vertex V in Q, I remove it from Q, I add it to A. But when I add it to A, I have to update these counters for all the predecessors of this vertex V, right? Because V is now added to A. So let's say this is, I don't know, let's say this is V. If V is added, then this predecessor has a new successor in A. So I have to increase the count. So for every predecessor of V, I increase this count. And of course, I keep track of this count only for vertices that are not already in A. If they're already in A, I'm done with them. Okay? Now, look at it from the point of view of a predecessor. Let's say I'm a vertex, and I just realized that one of my successors is in A. Okay? What happens? Well, let's apply the rule here. If I'm a vertex that belongs to player 1, and I have one successor in A, then I have to be in A myself as well, right? So here I say that if this predecessor was a vertex of player 1, add it to the queue so that we later add it to A. What is the other case? The other case is that this was actually belonging to player 2, but now all of its other successors were also in A. And so now when I'm realizing that this successor A is in A, I'm realizing that all the successors are in A. So if the number of successors that are in A is equal to the out degree, is equal to the number of all successors, then I also add this vertex W to my queue so that I later add it to A. And that's it. That's the algorithm. I don't really keep track of each of the A. I can find A in the end. And finally, I just return A, and of course, I can also return V minus A, which is B. Now, what is the runtime here? Well, the analysis is very much the same as the analysis you do for BFS. So every vertex is processed exactly once. Every vertex is added to this queue at most once, right? And then whenever you add a vertex to this queue, you process all of its predecessors. It is also processed once. So the total runtime is going to be n plus m, O(n plus m), where n is the number of vertices and m is the number of edges. Okay, so this is my runtime. Now, but this is basically O of m. Why is that? It's because of this small assumption that we had here. We assume that every vertex has at least one edge going out of it. So this means that we're assuming we have at least as many edges as vertices. So if it's O(n plus m, it's also O(n). So it's really linear time in the number of edges. Okay. What happens if I want to compute winning sets for the safety objective? If player 1 wants to remain in T and make sure that we never leave T. Well, this is the same as saying that player 2 wants to V minus T, right? So I can first just swap the players, solve it for player 2, see like when can player 2 reach v minus t? And from any vertex where player 2 can reach v minus t, player 1 cannot be safe in t. Otherwise, player 1 can be safe in t. So safety is basically the dual of reachability. And given that I have a linear time algorithm to solve reachability, I have a linear time algorithm to. Okay, quite easy. Nice. Okay, finally, we can get to what I actually wanted to teach today, which is Büchi. So let's talk a little bit about notation before we go into an algorithm for Büchi. So first of all, remember what Büchi is. Büchi is that I have a target set T, and as player 1, I want to reach T infinitely often. Okay? So it's not enough to just reach T once. I want to reach T, and I want to make sure that I come back to T infinitely many times. Okay. First of all, let's give a name to this sets A and B. So I've already told you that when we were doing reachability, I said that A is an attractor and B is a trap. But we have to kind of be more specific. So the set A was the attractor 1 of T, which means that it was the set of states from which player 1 could ensure that we will definitely reach T. Right? So if I'm in A, player 1 has a strategy that no matter what player 2 does, we will reach T. So I add this one subscript here. And then I would define attractor 2 of T in the same way. It's the set of states where player 2 can ensure T no matter what player 1 does. Okay? Now, and again, remember that our game had this format. So I had a vertex set, which was divided between player 1 and player 2, and I had a bunch of edges. Now, the first thing I want to do is that I want to define a subgame. I want to say, let's say I have my game, I want to remove some of the vertices, and I want to still have a game. Now, I can't just remove any set of vertices as I like. Because again, we had this extra condition here, and this condition seems very trivial, but it affects everything. So we had this condition that in a game, every vertex should have at least one outgoing edge. So if I just take any subgraph of my graph, it might be that I remove all the successors of a particular vertex, and then that vertex doesn't have an outgoing edge. So I cannot define a subgame. So here's how I define a subgame. I say that suppose that W is a subset of my vertices. If every vertex in W has a successor in W itself, then I can say, okay, we can delete all the other vertices and we have a subgame. So we can define the subgame at W like this. So G of W, the vertex set is W, and then the vertices that are owned by player 1 don't change. They're just V1, but intersect with W because we've deleted everything that was outside of W. And the same thing for player 2. So the vertices of player 2 are going to be V2 intersect W. And then the edges are just going to be the edges that had both of their endpoints in W. Okay. So now let me ask you some questions based on what we computed in reachability. So remember, our reachability algorithm started with T, and then it computed the attractor of T, attractor 1 of T to be more specific, and we called that A. Okay. So here's my first question. Does A induce a subgame? So do we have a subgame G of A with this definition? So my question is, if I remove everything outside of A, would I still have a valid game?
Yeah.
Why?
Oh my God, wait. Well, A is in P, then P may not have a successor in P.
Yes, you're right. So basically, we said that in order to have a valid subgame, every vertex should have a successor in that subgame. Now, if I have a vertex here, I'm sure that it has a successor in like a closer level to the center, right? So if and let's look at both players. If I'm here and I have a player 1 vertex, the reason it's here is because it had an edge to a level below, right? And if I have a player 2 vertex, the reason it's here is because it had several edges and all of them were to the level below. So for these cases, I'm happy, I have a game. But the problem is with A0 itself, with T itself. So it might be that I have in here, but all of its successors were outside of A, right? Because this was our base case. We were saying that if the vertex is already in T, I don't have any conditions about its successors. I'm winning anyway, right? So let's go back here. So if you look at these recursive definitions, in all of these cases, I'm talking about a successor that is already in A, at least one successor, except for this case. So if a vertex is in T, it might be that all of its successors are actually outside of A. So based on that, what happened? Okay. Yeah, based on that, A does not induce a subgame. So I cannot be sure that G sub A actually exists. It might be that G sub A does not exist. Okay, now I'm going to ask the same question, but I'm going to ask it about B now. And remember that B was this set, so A. Does B induce a subgame? Is there a subgame G sub B? Okay, so yes or no?
Yes.
Yes. And actually, you said something really nice there. B is a trap. So we can generally prove that any trap would give us a subgame. Why is that? So B was a trap for player 1. What does it mean when I say B is a trap? I think I had, do I have the definition of a trap somewhere? It should be somewhere here, but I can't find it. Anyway, so the definition of a trap was that no matter what player 1 does, player 2 can make sure that we remain in the trap. Okay, so here, if I'm in the set B and I'm at a vertex that belongs to player 2 has an edge that remains in B. Okay, if I'm in the set B and I'm in a vertex that belongs to player 1, all of its outgoing edges are going to be in B. So in any case, each vertex in B has at least one successor in B, and so I can define a subgame on B. Okay. So here's what I'm going to do now. I'm going to say, take this set B, and let's compute an attractor of B. But let's compute an attractor of player 2. Here is actually that I want to eventually go to Büchi. So A and B were the winning sets of players 1 and 2 for reachability. So if I were in A, I knew that player 1 could force the game to visit T. And if I were in B, I knew that player 2 can make sure we never visit T. Okay? But here's the thing. Suppose that I have a vertex somewhere here. And from this vertex, player 2 I can reach the set B somehow. Okay? But of course, on the way there, I might visit my target several times. But this would not matter if I'm doing Büchi. Because if I'm doing Büchi and I'm player 2, I would just say, let's reach the set B. And well, on the way, I don't care how many times I've seen the targets, but as soon as I reach B, I'm sure that I can make sure we never see the target, and then I win, because player 1 cannot ensure Büchi of T. Okay? So that's why I'm looking at this particular set. So let's call this set C, and C is going to be the attractor 2 of B, which means C is the set of all vertices from which player 2 can ensure that we will eventually reach B. Okay? So now the same question, does C induce a subgame? Yes or no? So we've already seen an attractor that doesn't induce a subgame. We've already seen that a trap does induce a subgame. Now this is another attractor.
Of the core, I think it is yes.
Yeah, this is also yes.
Because the core of the attractor has an outgoing edge inside the core.
Yes, exactly. So previously, when we were talking about this attractor, we saw that all of these cases have an edge that is inside the attractor itself. The problem was with the base case, right? But our base case here is a trap B. So I don't have the problem with the base case anymore. So another way of looking at this is that, let's say this is my set. And it's really hard to write with the mouse, sorry. And let's say that I compute its attractor, and let's say this is the attractor C. Now, if I have a vertex that is already in B, I know that it has a successor in B because B was a trap, because I knew that GB exists. And if I have a vertex that is in C, but it's not in B, at the very least, I know that there is a path from this vertex to B, right? Because, I mean, player 2 can ensure that we will reach B. Right, and this path is going to have, I'm just going to take the first edge out of this path, and it's going to remain in C, of course. And so this vertex also has an edge, an outgoing edge, where the target is also in C. So, yeah, nice. So we have this case where we are taking the attractor of B, and we can define on that attractor. Now, what if I take the complement of C? What if I take V prime? I'm going to call it V prime, but it's the complement of C. It's basically V minus the attractor 2 of B, which was C. So if I take the complement of C, can I define a subgame on that? Okay, people are saying yes, but why? Yes, because it's a trap. Because the complement of every attractor is a trap, right? I mean, it's a trap for player 2. It's not a trap for player 1, but who cares? I'm just changing the order of the players. I can always define a subgame on a trap. So this one is also fine. And by the way, these things work even if these sets are empty. Even if V prime is the empty set, that's fine because I can have the empty game. And okay, if that sounds a bit counterintuitive to you, just look at the definition of the game and see what happens if the set V is empty. So V is empty, V1 and V2 would be empty, and every vertex has at least one outgoing edge because we don't have any vertices, right? It's vacuous. Because I don't have any vertex, every vertex has an outgoing edge. Okay. So I did all of this so that I can tell you that we cannot talk about a subgame on A, but we can talk about subgames on B and C and this complement of C. And just remember these definitions because I'm going to use the sets A, B, and C many times now. So A is the set of vertices from which player 1 could make sure we will reach T. B is the complement of A. B is a trap for player 1. It's the set of vertices from which player 2 can ensure we will never reach T. And T was our target set. Now, the attractor 2 of B. So B was the set of good vertices for player 2. C is the set of vertices from which player 2 can force us to visit one of the vertices in B. Okay? So now we're going to talk about the classical approach to solving the Büchi objective. So let's say that the objective of player one is now Büchi of T. So I have this set T, and player one wants to game sees this set T infinitely many times. Okay. So again, the same definitions here. I have this set A, and from anywhere in A, player one can make sure that I will visit T at least once. I have the set B, and from anywhere in B, player two can make sure that I don't visit T at all. And then I have C. So let's draw it. I set C. Okay. And it will include all of B. So I'm going to call this C. C is the set of vertices where if I start the game there, player two can ensure that I will eventually reach B. Now, while I'm reaching B, it might be that I go through T a number of times before I reach B, but that's fine, right? Because player one's visit T infinitely many times, and we're assuming a zero-sum game, so player two is fine with visiting T a finite number of times. Okay. Now, here's what I claim. I claim that for every vertex in the set C, player two has a winning strategy. Okay, give me this strategy. Oh, well, the objective of player one is Büchi of T. So player one wants to see T infinitely many times. And it's zero sum, so player two wants to make sure we see T only a finite number of times. Okay.
Oh, we can let T by eventually goes to B, and then we don't with T.
Yes.
Player two.
So basically, if you're player two, and if the game starts in C, you have a strategy to make the game will reach B. So you just play that strategy, and you play it until you reach B. Now, again, on the way, you might have visited T a finite number of times, but that doesn't matter. You're fine with visiting it a finite number of times. But then what happens when you're in B? As soon as you're in B, by definition of B, you know that B is a trap for the other player, so you can keep the game in B. So as soon as you reach B, you switch your strategy to the strategy that was for keeping the game in B, and then you just remain in B forever. So it's a mixture of the two reachability strategies. And this gives you a strategy for this case, for the case where basically you want to do Büchi of V minus T. Okay. So what does this mean? This means that if I want to find the set of vertices where player one wins and the set of vertices where player two wins, at the very least, I know that player two wins everywhere in C. So I can mark all of this as part of the winning set of player two. Okay. Now, the funny thing here is that it might also include parts of T. So it might be that you have a target vertex, but if the game starts from that target vertex, player two can ensure that you see target vertices only a finite number of times. So this is how our diagram looks like right now. Okay, so I know that from every point in C, player two has a winning strategy. What about the rest of the graph? So what happens here? So this part is like V minus C. Okay, so you can see the answer already there. And the answer is that, well, this is just a smaller game. So I'm going to solve it recursively. Okay. But why does that make sense? Why does it make sense to look at this smaller? We will come back to that. But basically, the idea is that if I'm in this smaller game, player one would never want to go to C because player one knows that if he goes to C, player two wins. So player one keeps us in this smaller game. That's why we can recursively solve over this subgame V minus C. Okay. So this is now, okay, and I can write this in a recursive variant, or I can write the code in a way that doesn't use recursion at all. So here's how I can write the pseudocode without recursion. I just keep track of my current game, and my current game is going to get smaller and smaller. Okay, so I have T0, and generally I'm going to have Ti, and I'm going to have, okay, sorry, it's J. So during this algorithm, I'm going to have a game GJ, which is like iteration J. And then in this game, player one's objective is to have Büchi of TJ. So to see TJ infinitely many times. Now, initially, of course, T0 is just T and G0 is the entire game G. And then I keep track of two sets. I keep track of W2, which is the set of states from which I know player two has a winning strategy. And then I will also have W1, which is the winning set of players. But I keep track of W2. I just compute W1 at the end. Now, what do I do? Every time I basically do this same argument that I had here. I say that, well, let's say that AJ is the attractor one of TJ. So AJ is all the states from which player one can make sure we reach TJ. And then I take its complement. This is the trap that player one. And then I take the attractor two of that trap. So CJ is the set of states from which player two can ensure that we reach BJ. And if we reach BJ, then player two can ensure that we will never reach AJ. Right? And so I know that based on this simple strategy that I had here, player two will win in CJ. So I just add CJ to the winning set. I say W2 is W2 union with CJ. Okay. Now, again, I found that player two wins in all of these places. So I'm going to say now my game is going to be the sub game on the remaining part. So I'm just going to now solve this part. So I'm going to say VJ plus 1 is just VJ minus this CJ, because I already know that player 2 wins in CJ. And I also update everything else. So the target is going to be minus CJ, and I mean the game itself is updated. Now, for how long should I continue this? Well, I have a 4 here that basically goes to infinity, but it's like I have to do this only until CJ is empty, right? So every time I'm just finding more and more vertices where player 2 can win. If at some point I cannot find any more vertices where strategy, I just give up. I say that's it. That's okay, and I break. So, and at the end of it, this is now the controversial part. I say that the winning set of player 1 is just the complement of the winning set of player 2. Okay, so my algorithm is kind of assuming that the game is determined. Now, here's the thing. The part that is trivial is that if I have a vertex that is in W2, player 2 is going to win, because I gave you the winning strategy, right? What's not so trivial is that if I have a vertex that is in W1, a vertex that is in complement of W2, then player 1 has a winning strategy from that vertex. So we have to prove this now. Okay. Why does player 1 win in W1? Let me just draw another case for you. Sorry. So remember, we had this set T. This was our target set. Player 1 wants to visit T infinitely many times. Then we had the set A, and A was the attractor 1 of T. So from anywhere in A, player 1 could ensure that we will visit T at least once. And then B was the complement, and we said that B is a trap. So if we are in B, player 2 could ensure that we will always remain in B and we will never cross this boundary here. Okay. Now, what did we do? We computed a bunch of sets. So we're calling them like C1, C2, and so on. So first I computed the first set. Let's do it like this. And this was, let's say, my set C1. Then I computed a larger set, which was C2 and so on. But let's just look at C1. So this is the first time that I'm computing C. And this is the set of vertices from which player 2 can reach B. Player 2 can ensure that if I start anywhere here, including inside of T, the game will eventually reach B. And when the game reaches B, player 2 will just trap player 1 and then win. Okay? So it's pretty obvious that in C1, player 2 wins. Now, I want to consider a game that starts outside of C1. And I want to see if this game would ever reach C1. So consider all the edges that go from outside of C1 to C1. Because if my game is going to reach C1, I have to take one of those edges. Okay, so some of these are from vertices that belong to player 1. So let's say these are vertices belonging to player 1, and they have edges into C1. Okay, so consider this vertex. Do you agree that it also has an edge that doesn't go into C1? Yes, because C1 was an attractor. So if all the edges of this vertex were going into C1, then this vertex itself would be added to C1. So this vertex definitely has an edge that is going somewhere else, not into C1. Now, let's say you're player 1. If you're at this vertex, you will never take the edge that goes into C1. Right? Because that's stupid. If you take that, then player 2 wins. You know that player 2 wins from everywhere in C1. So we are sure that if we are player 1 and we are here, we will remain outside of C1. Okay? So in other words, I can delete this edge and nothing changes in my game. Because that was an edge that player 1 would not take anyway. Okay. Now, let's consider the same thing, but let's say I have a vertex here that belongs to player 2. I claim that this vertex cannot have an edge to C1 because C1 was the attractor 2 of B. If this vertex had an edge to C1, then it would be already put into C1 by definition, because player 2 wants to reach B. He knows that he can reach B from C1. If he had like this, he would take it and then he could reach B from this vertex as well. So this vertex would also be in C1. So if I have a player 2 vertex here, all the edges are going out. None of the edges are going to C1. So in other words, it makes perfect sense to say that player 2 wins in this part, and the remaining game is completely independent. So in the remaining game, you win if and only if you can win without entering C1. Okay, because player 2 cannot enter C1 from the remainder of the game, and player 1 would not enter C1. Okay, but now let's continue this. So let me erase these. I had this set C1, and then I had this other game to the right. And based on that, I computed another set. Let's call this one C2, where again, player 2 wins. And then I computed another one, C3, so on. And let's say I go all the way to Cn. Okay. Again, I can say the same thing. I can say that in all of these, player 2 wins. But now I want to say that if the game starts somewhere here, outside of all the C sets, player 1 wins. Okay, so the game has started outside of all these C sets. Give me a strategy for player 1. Give me a winning strategy for player 1.
Just don't go into the C.
Yes, so our strategies are always super easy. The strategy player one is just never going to the C's, right? But is that enough? Because, well, I might have some part of T remaining here, right? So if I just say don't go into the C's, it might be that I'm visiting this small part of T infinitely many times. Actually, let me make this shape a little bit nicer. So let's say that this is Cn. So I know that in all of these parts, player two is going to win. And I know that if I'm outside of these C sets, I should never enter them as player one. But is that enough to make sure that I win the game? Because it might be that I choose a strategy that never exits this part of the game, but nevertheless, I visit this part of the target set infinitely many times. So you have to somehow ensure that doesn't happen. How would you do that?
It should include the T as well.
Give me an argument for this. Okay, so let's just look at this subgame. What is this subgame? This is a subgame in which when I computed that C, the C set was the empty set, right? Because otherwise I would keep expanding my C. So let's just zoom in to this last subgame. Know that we will not exit the last subgame, so that's good. I can really zoom into it. I'm going to reuse the same figure, but just imagine that this is not my initial game. This is the last subgame, okay? So I have this last subgame. It's a bit hard to erase here. Okay. So I have this last subgame. In this last subgame, I have some remaining part of T. Then I have A and I have B. What can I say about B? I know that when I computed attractor 2 of B, that was empty. I couldn't find any new vertices where player 2 won. So if attractor 2 of B is empty, B itself has to be empty. Do you agree with that? Because B is a subset of its attractor. That was, again, like the first line of the definition of an attractor. So this B is the empty set. Now, if B is the empty set, what does it mean? It means that A is the entire game. So all the vertices in my graph are in A. But A was the attractor of T. Right? So it means that no matter where I start my game, player one can ensure that I will reach T. One has a strategy for that. Because again, A was the attractor one of T. But then player one can just play this strategy all the time, right? So if I'm player one, no matter where the game starts, I just go ahead and play my reachability strategy until I reach T. Now, the game is going to stay in T for a while, and I'm happy as long as it's in T. And at some point, if we go outside of T again, I again apply my reachability strategy, and then I will do this forever. So this is a winning strategy for player one. So this shows that in the remaining part of the game, in the sub-game where I couldn't find any new C vertices for player two, player one has a winning strategy. Okay. Are these strategies memoryless? Okay, why?
Don't care about the previous.
Yes, so basically player one strategy is memoryless because it's just a reachability strategy, right? We're just using the same strategy. And we knew that it was memoryless there. But what about player 2? So for player 2, I have a similar case, right? It's always like it's a combination of two strategies, but it's a combination of two memoryless strategies. So my strategy for player 2 was always that if you are in the set B, if you're in one of these traps, keep staying in the trap. And that was a memoryless strategy. And we said that if you're in C but not in B, just do the reachability strategy to B. And that was also memoryless. And then when you reach B, then you do the trap strategy. Great. So we just proved the correctness of this algorithm, and we proved two other things. We proved that our game is determined because the winning set of player 1 is the complement of the winning set of player 2. And we also proved that it's determined with memoryless strategies, which is again great. So here's another example for that 1/4 of your homework. So what's the runtime here? How much time does my algorithm take? No, it's more than that. Right. So we can say that every iteration of the while loop takes linear time, because every iteration of the while loop is basically our reachability algorithm, just computing attractors, right? It's computing two attractors, but who cares? It's just a constant. So every iteration takes OM time. But how many iterations do we have? You're saying at most n. Why do we have at most n iterations?
Each time we add at least one word to the CJ, meaning that we will decrease the whole size by 1.
Right. Okay. Well, I would rather talk about W2. So every time we're adding W2, I agree that it's because it's in CJ. So W2 is getting larger and larger in every iteration, and it can at most have a size of n. At most, we can add all of our vertices to W2. So we're going to have at most n iterations here. So the overall runtime is O n times n. Good. I've already answered these two questions. How can we find these? I just told you the strategies, and the game is determined, and it's also memoryless determined, which means that it's determined with memoryless strategies. So my final question is, how would you solve Kobuki?
And then take the company.
Yes. So if the objective of player 1 is Kobuki of T, this means that player 1 wants to ensure that all the vertices that are seen infinitely many times are in T, which means that player 1 wants to ensure that all the vertices outside of T are seen only a finite number of times. But then if we look at it as a zero-sum game, this means that player 2 wants to make sure that there is at least one vertex outside of T that is seen infinitely many times. So if it's zero-sum and one is Kobuki of T, then the objective of player 2 would be Büchi of V minus T. But we know how to solve Büchi, and we know that Büchi is determined. So we can just solve Büchi of V minus T, and then we just swap the answer like from yes to no and no to yes, and then that gives us the answer here. In this session, we're going to see a faster algorithm for solving the same thing that we solved in the previous session. So we're going to consider Büchi objectives, and then we're going to also extend our algorithm for Büchi objectives to general parity objectives. So I'm sure you still remember this. So we're going to have two different types of really important objects here. we have attractors, and we also have the complement of attractors, which were traps. And up until this point, the only kind of trap that I've really talked about was that I took this set T, and then I computed the attractor of T, and then I said, let's look at the complement, and that's a trap. But let's now look at more general traps. So my trap doesn't necessarily have to be the complement of this particular attractor. So here's the formal definition of trap again. I say that a set S, subset of my vertices, is a trap for player one. If, first of all, there is no way player one can exit from the trap, so there is no player one vertex in the trap that has an edge to outside of the trap. And secondly, if every player two vertex in the trap has a successor in the trap itself. So if it's player two's turn to play and we are in the trap S, there is a successor that is also in S. So player two can ensure that we will remain in S forever. Okay. And of course, normally I want to make sure that my trap does not include any of the target vertices, because I want to make sure that the first player cannot reach the targets. That's like the whole point of having a trap. So I would say things like, this is a trap of player one out of T, which means that the intersection of the trap S with the target set T is empty. Okay, great. So let's just look at the algorithm that we saw for Büchi one more time, and let's just focus on the traps. Let's see what we're doing here. So we had this set of target vertices T, and we said that first we compute the attractor of T for player one. So this is the set A. And from anywhere in A, player one can ensure that we will reach T. And then we said, okay, let's take the complement of this attractor, and let's call that B. And we said this B is a trap. Okay, so this is a trap. I have to stop writing with the mouse. And then the idea was that not only player two can win starting from anywhere in B, but actually player two can win starting anywhere in the attractor two of B, right? And the strategy was also very simple. The strategy was that if I'm inside this trap and I'm player two, I make sure we will never leave the trap. And this makes sure I will never have to visit T. And if I'm in C, let's say this was C, which is the attractor two of B, as player two, I would first make sure that we will reach B, and then I'll apply the same idea as before. I'll just keep the game in B and not let it go out. Okay. But again, what I want you to really focus on here is that B is a trap. And what happens if B is empty? If B is empty, then C is also empty. And that's what we used in the previous session to show that, like, in the remainder of the game, player one has a winning strategy. So based on this, and of course, this was a recursive algorithm, we would continue solving it in the rest of the game as well. But okay, this was the pseudocode that we had for this. So basically, every time I computed an A, a B, which was the trap, and then I computed the attractor of B, which was C, and then I would add C to the winning set of player two. And now I want you to, again, deconstruct the runtime argument that we had for this algorithm. So the runtime argument was that in every iteration, I'm adding something to the winning set of player two. So I can have at most n iterations. And then I was also saying that in every iteration, I'm spending OM time, because these attractor computations, these were just reachability, and I know how to do them in OM. So the total runtime is ON times n. In this session, we want to decrease it to ON squared. And this is actually a huge decrease, because you can imagine that if you have a very dense graph, M can be n squared. And so this is actually a cubic algorithm in terms of n, whereas this is just quadratic. Okay, now which are the parts where I can probably get an improvement? when I was doing the runtime analysis, I said that I have n iterations and each iteration is taking all m time. So if I want to somehow obtain an improvement, I have to either reduce the number of iterations or I have to reduce the amount of time that each iteration takes. Okay. So first, let's talk about the number of iterations. If I want to reduce the number of iterations, what do I need? If I want to have a better bound on the number of iterations, I need to say that this set W2 increases faster in a sense. Its size increases faster because right now in my analysis, I'm just saying, okay, every time I'm adding something to W2, but I'm not really caring about how big this thing is. I'm just saying that I'm adding at least one vertex to W2 each time. But ideally, I want to add a lot of vertices to W2. That's the first thing. And that gets us to the point where we say that, well, if that's the case, if I want to add the largest number of vertices, this means that I want to have the largest possible set CJ here. But right now, we're not using that at all. And actually, right now in the analysis that we have here, it doesn't really matter what CJ is, as long as we're sure that player 2 has a winning strategy. But what's even harder is improving the second part of the runtime. So imagine that I want to spend less than m time in every iteration here. So how can I do that? Well, if I'm computing attractors, at the very least, I have to process the reachability, right? I have to go over the graph at least once. I mean, even just reading a graph with n vertices and m edges is going to take linear time. So the only solution I can have if I want to reduce the m part of this runtime is to work on a smaller graph. So somehow I want to avoid working on my original graph, original game, and instead find a subgame that has fewer edges, and then work on that subgame. Okay, so these are the two ideas that I want to have in mind. I want to find bigger traps, let's say, and at the same time, I want to do it in smaller graphs. Okay, so the first thing I want you to notice here is that if I take this algorithm and if I don't care about the runtime, if I only care about the correctness, instead of this BJ that I have here, I can put any trap, right? So previously in the classical algorithm, I said that I take T, I take the attractor of T, and then I take the complement of this attractor, and I call that B. But instead of taking the complement of this attractor, I could take any other trap. As long as it's a trap outside of T, everything else would work. Because when I was giving the strategy for player 2, I was saying, if you're in the trap, just remain in the trap. And if you're somewhere else in C, not in the trap, first reach the trap and then remain there. So the only thing, the only property of B that I really used here was that B is a trap of player 1 outside of T. And yeah, so instead of this BJ here, I don't have to put VJ minus AJ, I can put any trap. This is helpful because this means that I don't have to necessarily compute this attractor. You see, the most time-consuming part of every iteration was that I had to compute these attractors, and then I had to take their complements. But if instead of BJ, I can just put any trap, and if I somehow magically have a faster way of finding traps, then I don't need to compute AJ at all. So that's, again, one of the first ideas that I want. And so the other point is that, at least in the analysis that we did initially, where we said that this W2 is increasing in size and we didn't care about the amount of increase, there is really no benefit in finding the largest trap. So in a sense, this BJ is the largest trap, right? So my algorithm, my original algorithm here is finding the largest trap, but then in my runtime analysis, I don't have a bound on the size of this trap. So maybe even the largest trap is just giving me one new vertex. So I'm not benefiting from computing the largest trap here. So what do I want to do? I want to, first of all, replace the trap BJ with some other trap. But secondly, I want to also have a runtime analysis that takes the size of the trap into account. Now, why do I say the size of the trap BJ and not CJ? Because it's just too hard to talk about CJ. Okay, and you will see soon. But what do I know? If, let's say, my trap BJ has k vertices, what does that tell me? That tells me that I will find at least k new vertices where player 2 is winning. So CJ always includes BJ. So if I can say that the size of my trap is some number k, I can basically say that this one iteration increased the size of W2 by at least k. So based on all of these, this is my wish list now. This is the problem that I want to solve, hopefully. I want to find the trap, and this is my input. My input is just an arena. It has n vertices and m edges. And I also have a set of target vertices, T. Now, I want to find a trap of player 1 outside of T, but this is the part where things get interesting. If this trap has size k, I want my runtime to be ONK. So I want to find an algorithm whose runtime is bounded by the size of the trap that it finds. Now, why do I want to do this? Because I want to say I spend ONK to find the trap of size k. But when I find the trap of size k, this W2 increases in size by at least k. So my overall runtime would be at most n times the sum of all the k's. But the sum of all the k's is at most n, so my overall runtime would become n squared. So that's why I want to find a trap of size k in ONK, ideally. Does this make sense to everyone? Are you fine with this?
So if we do that, we want to take the abstraction of the trap we find.
No, we do that anyway. But that part doesn't take that much time.
Like CA.
Okay, so here's the thing. Let's say I don't have to do this. And to find a trap here, I'm spending ONK, and I'm finding a trap of size k. Okay, so computing this CJ, what happens when I want to compute CJ? I'm basically doing my reachability algorithm with the queue and everything, but I'm just putting this trap as the initial elements in my queue, right? But everything that I find in that algorithm will be in CJ and will be removed. So the total runtime that I spend on computing all of the CJs is OM, right? In all of the iterations, I'm not spending OM per iteration, I'm spending OM overall for all the CJs. So this part is fine. This part is not taking that much time. The part that I really had to get rid of was this part.
But also if we remove the line finding the section of PGL, the algorithm would still work with the same sound, right?
If we remove that, yes. Yeah, it will not affect the runtime. I can find the same runtime. But let me see. Does the correctness proof go through? So here, basically, you're saying instead of removing C, let's remove B. It's possible that the correctness is affected by that, right? Because if you are in C, player 2 has a winning strategy. But if you just remove B, it might be that from a vertex here, player 2 no longer has a winning strategy. Can you prove that doesn't happen? If you prove that doesn't happen, then you don't need to compute C. I'm not sure, but anyway, my point is that the computation of C here doesn't really affect my total runtime, so I don't care. But yeah, anyway, what's really important for us is that I want to basically spend ON time for finding each one of the vertices that is added to the winning set of player 2. so that I can overall say that I'm going to add at most n vertices to the winning set of player 2, so my overall runtime is n squared. Okay. So now this is my goal. This is what I want to solve. I'm given a graph G, and okay, I have a set of target vertices. I want to find a trap of player 1 outside of this target vertices, and I want to say that if my trap size is k, I want to spend ONK. And again, it's very important. This is n. This is the number of vertices, not the number of edges. Number of vertices times k. Okay. Now, this is the same problem that I talked about a few minutes ago, which is like, if I want to spend less than m time, if I want the time to not depend on the number of edges, I have to somehow sparsify my graph. I have to somehow find a subgraph that is smaller so that I can work with that smaller subgraph. Because if I want to work with all of my edges, I'm going to spend a time that is at least linear in the number of edges. Okay, so this is the very simple idea that I have. I'm going to discard some of the edges. I'm going to just keep a few edges, and then I'm going to try to find a trap in this limited graph. Okay, but let's just define what this means. So this is what I call a subgraph trap. So let's say that I have a set E prime, which is a subset of my current edges. And basically what I want to do is that I want to trap player 1 not only inside a set of vertices, but also inside this set of edges. Okay, so let's say that I have E prime and I have S. So S is a subset of vertices, E prime is a subset of edges. I want to trap player 1 so that he cannot reach any vertex outside of S and he cannot reach any edge outside of E prime. Okay, and this is called an E prime trap. And of course, I want to make sure he doesn't reach T as well. So T is the target set. So T intersect S is going to be the empty set. Okay, this is basically the same as the definition of a trap. It's just that I want to say player 1 cannot take any edge outside of E prime. So I say for every vertex V that is in this set S, if that vertex belongs to player 1, if it's in S intersect with V1, then all of the outgoing edges must be in E prime. Okay, this ensures that player 1 can never take an edge that is not in E prime. And then the rest of it is just the definition of a normal trap. It's that I should not have any of my target vertices in my trap. And also for every vertex that belongs to player 1, all the outgoing edges remain in the trap. Now, this one is going to change a little bit. And it says that for every vertex that belongs to player 2, there is an outgoing edge that keeps us in the trap, but this outgoing edge should also be in E prime. Okay, so basically I'm saying I'm player 2, I want to trap player 1. I can get rid of some of the edges, but I have to make sure that I can trap him even without the edges that I got rid of, using only the edges that are remaining there. Okay, so that's the only thing that changes here. Okay, based on this, let's actually talk about the subgraphs that we want to have. And so remember, the intuition here is that I want to define a bunch of subgraphs. I want to define subgraphs that have very few edges. And then I want to trap player 1 in these subgraphs instead of the original graph. Okay. Okay. Here's how we're going to do this. This is going to sound really bizarre and weird at this point, but just understand the definition, and at some point in the proof, you see why this definition helps us. Okay. So here's what I'm going to do. I'm going to just give an order to the edges in my graph. So basically, I'm going to give numbers to them. I'm going to number them E1, E2, and so on. But this numbering has a particular peculiarity, and this is the way I'm numbering. So I'm saying that first find all the edges UV such that U is in V2, but it's not in T. Okay, what does this mean? This means that I'm taking all the edges that are going out of a player 2 vertex. Okay, a player 2 vertex that is not a target vertex. So I'm numbering all of my edges, but the only constraint is that first I find all the vertices that belong to player 2 but are not targets. And I'm first numbering all of the edges that are going out of these. And then I'm numbering the rest of my edges. Okay, so I'm just giving priority to these particular weird types of edges. And you'll see how this helps. But other than this, I don't have any other constraints. So I have many different ways of numbering the same graph. Okay. Now, here's how I'm going to define my subgraphs. And this is called the hierarchical decomposition because I have a bunch of subgraphs, and I'm going to call them G0, G1, G2 to G log n. And again, intuitively, the idea is that I'm going to start with a graph that has almost the same number of edges as vertices. And then every time I'm going to almost double the number of edges that I have. And that's why I have at most log n. Well, it's log n, I don't know, 2 log n or something like that. It's O log n, it's not exactly log n. But the number of graphs that I have is like a factor times log n. Okay, now how do I actually define these graphs? Or actually it might be log n plus 1, I don't know. Okay, so I say that my graph GI basically has the same set of vertices as my original graph, but it only has a subset of the edges. And I include an edge in this graph GI if and only if the edge is one of these two cases. So the first case is that this is an edge from U to V, and the out degree of U is at most 2 to the power of I. So if I have a vertex U like this, and the number of edges that are going out of U is at most 2 to the power of I include all of them in my GI. Okay. For the second case, I'm going to look at the incoming edges of a vertex. I'm going to say, look at a vertex V and look at all of its incoming edges. It might have a ton of incoming edges, but I'm going to take the first 2 to the power of I of those edges and include them in GI. Okay, so an edge will be included either if the starting point of the edge has only 2 to the power of I or less outgoing edges, or if this edge is one of the first 2 to the power of I in edges of its endpoint. Okay. Any questions? Are you all fine with this? So how many edges does this GI have? How many edges can I have in my graph GI? Someone please answer me. Well, for every vertex, I'm going to add at most 2 to the power of I outgoing edges and at most 2 to the power of I incoming edges. And I'm counting some of these twice. So I have at most n times 2 to the power of I plus 1 edges. Right? But if I want to use the O notation, it's just O n times 2 to the power of I. That's the number of edges that I have. Okay. Now, why is this interesting? This is interesting because I'm basically starting with a graph that has ON edges, and I'm just doubling the number of edges every time, almost. Not exactly, but almost doubling it every time. Okay, let me show you an example. Let's say that this is my graph, and let's say player 1 is circle and player 2 is square. Okay. So the first thing I do is that I give a number to each one of the edges. But the rule was that I have to first start with the edges that go out of a player 2 non-target vertex. Okay. So this is a target vertex, so I don't care about this. This is the only player 2 vertex that is not a target vertex. So first I number all the edges that go out of this. So 1, 2, and 3. And then I can number everything else in whatever order I like. So I just picked a random order and I numbered them. Okay. So now let's see how we create these subgraphs. So let's say I want to create G0 because this is a small graph anyway. I'm going to only show you G0. So in G0, I'm first going to find all the vertices in the original graph that had an out degree of 1 or less, 2 to the power of 1. And I'm going to put all of those edges. So for example, if you look at this node, it had an out degree of 1. So that edge is going to be in my G0. And these two nodes, they also had an out degree of 1 each. So this one had an out degree of 1, this one had an out degree of 1. So these 3 edges are included for the first reason. And then I'm going to say for every vertex, look at the edges that come into it and take the first 2 to the power of I. So in this case, take the first edge that comes into every vertex. Okay. So for 9, the only edge that comes into it is 9. Sorry, for this T, the only edge that comes into it is 9. This one doesn't have any incoming edges, no problem. So this one has a bunch of incoming edges. It has 6 and 8, but I'm taking the one with the smaller number, so I'm taking 6. This one has 3 and 10, so I'm taking 3, and so on. So this one actually has 2, 5, and 7, so I'm taking 2. So you see 2 is included here because among the incoming edges to this vertex, to this one, 2 had the smallest number. But 5 is also included because this vertex had only 1 outgoing edge, and that was 5. So I have both of them. And this is my graph G0, and we've already shown that in general, the graph GI has O(n) times 2 to the power of I edges. Okay, now in this case, of course, my original graph was already small and sparse, so my G0 looks very similar to the original graph. But in general, that would not be the case, right? In general, my G0 is actually much sparser than the original graph. And of course, as I continue, my graphs are getting denser and denser until my G log n, or maybe G log n plus 1, becomes the original graph G. Okay. Now, if that was not complicated enough, I'm going to do one more complication, and I'm going to color the vertices. Okay. So I take my graph GI, and I color the vertices with 3 colors. So here's what I do. First of all, the vertices that have a very low degree, they're going to be colored white because they're not important vertices. And the way I define that is that if the number of edges that are going out of this vertex is at most 2 to the power of I, then this vertex is white. Okay. And then for the high degree vertices, the ones that have an out degree of more than 2 to the power of I color them based on which player they belong to. So I color them blue if they belong to player 1 and red if they belong to player 2. So from now on, whenever I say white, it means a vertex with low degree. Whenever I say blue, it's a high degree vertex of player 1. And red is a high degree vertex of player 2. Okay. And this is, again, an example. So these are low degree vertices. They each have just 1 outgoing edge. So they're colored white. And this one has more than 1. This one has 3 outgoing edges, but it's a player 2 vertex, so it's colored red, and this one is blue. I don't know what's happening here. This is wrong. This should be white. Okay. Oh, no, sorry. Yeah, I have to look at the degree in the original graph G. So I'm not looking at the degree in this graph. I'm looking at the degree in the original graph. But I'm doing the coloring in the smaller graph because I can't make things easy. So this one is blue because in the original graph, it had an out degree of 2. Okay. So another way of looking at this is that if I've included all of the outgoing edges due to the first rule here, then the vertex is white. Otherwise, the vertex is either blue or red based on who owns it. Okay. finally, we want to find traps. And we want to find traps in these subgraphs, of course, because otherwise what would be the point of defining these subgraphs? So I'm going to define a set xi, and this is going to be a set of vertices. And these are the vertices that are either blue in GI or they are red in GI, but have no outgoing edges. Okay. Now, why do I care about these vertices? I want to find a trap that not only traps player one away from the target vertices, but also traps him inside GI. Now, the problem is that if player one can reach any of these two types of vertices, or if the game can reach any of these two types of vertices, then player one can break out of GI and go to the rest of the original graph. Okay, now, why is this? First of all, what does it mean if a vertex is blue in GI? It means that this vertex belonged to player one, and it had more than 2 to the power of I outgoing edges. But if that's the case, it might be that I'm not including one of the outgoing edges in my graph GI. So it's possible that player one takes an outgoing edge from the graph GI from this blue vertex that basically goes outside of GI. It's an edge that exists in G, but not in GI. How about this one? This is a red vertex in GI. So this is a vertex that belonged to player two. And in the original graph, it had more than 2 to the power of I edges going out of it. But for some reason, none of its outgoing edges are in the current graph GI. So it means that if the game ever gets to this point, player two is forced to go outside of GI. Right? So I want to make sure that I find a trap in GI such that we never reach these two bad cases, so that we really remain in GI. Okay. Now, how do I do this? Well, finding traps is easy. We know how to find traps. That's basically the same thing that we used to do for reachability. So I start with my graph G0. I look at E0, and I try to find a trap of player one outside of T union with X0. So T was the set of target vertices, and X0 were these weird vertices here where if I got to them, I could exit the current subgraph, and I didn't want to allow that. Okay, so if I find such an S0, I would be very happy, and I just output it as my trap. Okay, if not, I just try with the next graph. I try with the graph G1, and I continue this. So eventually I will find the trap, because my last subgraph is my original graph, right? And if there is a trap in the original graph, in the last iteration, I will find it. But why do I even care about this? Why am I doing these weird things? Why am I trying to trap the player inside these subgraphs first? It's basically because of the runtime. So let's just answer these questions here. How to find a subgraph trap? Easy. We just do reachability in that subgraph, right? But what is the runtime if I do reachability inside one of these subtraps? So I know that my, subgraphs. I know that my subgraph I has n times 2 to the power of I edges. So if I do the reachability there, it's going to take me only O n times 2 to the power of I. Okay. Whereas if I did reachability in the original graph, it would take n plus m. So I'm hoping that n times 2 to the power of I is much smaller than n plus m. Okay, that's what I hope. I have to prove it, of course. So I know how to find a subtrap. I know how to find a subgraph trap, and I know how much time it takes. But let's just go over this again. Let's say I find a subgraph trap outside of T union Xi. Why is this a trap in the original graph? It's a trap in the original graph because I cannot reach T, of course, and I cannot reach any of these vertices, so I cannot exit GI. So basically, the game is really constrained to GI. Okay. And of course, I told you why it finds a trap at all, because eventually my largest subgraph is just my original graph. So in the worst case, I'm just wasting a ton of time on the smaller subgraphs, but at the end, I'm finding a trap in the largest. Okay. But from now on, let's assume that we find our trap at iteration I. So I've spent n times 2 to the power of I time, and I found my trap. Okay. How big is this trap? And by the way, the ice iteration takes n times 2 to the power of I, but also the first I iterations combined also take n times 2 to the power of I, because the sum of powers of 2 is always smaller than the next power of 2. Right? Okay. So how big are these traps? Here's my claim. I am claiming that if I find the trap Si, and if I find it in the graph Gi, then my trap has at least 2 to the power of I minus 1 vertices. Okay? So before I prove this, do you agree that if I prove this, then I have an ON squared algorithm for Büchi? Because the amount of time that I'm spending is n times 2 to the power of I, and I'm finding a trap that has 2 to the power of I minus 1 vertices, so half of that, right? So basically, to find a trap of size k, I'm spending ONK time, and that's exactly what I needed to have n squared time overall. Okay, let's prove this. I'm going to do a casework, but I'm going to ask you to fill in for each one of the cases. So this is what I'm assuming. I'm assuming that I found my trap Si in iteration I of the algorithm. So I found my trap in the graph Gi. Okay. This means that I couldn't find the trap in Gi minus 1, because if I could find the trap in Gi minus 1, I would just stop there. Okay. Now, here's my first case, and I want you to solve this case. The first case is that we have a player 1 vertex U, and this U is inside the trap, but it used to be blue in the previous iteration. Okay. What can I say if I have a vertex like this? So what does it mean that it was blue in the previous iteration? It means that it belonged to player 1. And it also means that the out degree was more than 2 to the power of I minus 1. So in the original graph, it had at least 2 to the power of I minus 1 edges going out of it. Okay, what does that say about the size of my trap in the next subgraph? I'm just going to wait for you to figure it out. So this is a trap, and this is a player 1 vertex that is inside this trap. What does that tell you? Yes, exactly. So since this is a player 1 vertex and it's inside my trap, and remember, we've already proven that this is not just a trap in Gi, it's also a trap in G, right? So all of its successors should also be inside this trap. But we know that in G, it has more than 2 to the power of I minus 1 successors. So here it has also at least 2 to the power of I minus 1 successors that are all inside this trap. So the size of the trap is at least 2 to the power of I minus 1. Because there are just 2 to the power of I minus 1 successors of this vertex that are in the trap. Okay, first case is solved. Well, the second case is, of course, if we don't have a blue vertex. So this is my second case. Suppose that I have found my trap in GI. So there was no such trap in GI minus 1 that my algorithm could find. And let's assume that all the player 1 vertices that are in this trap used to be white before in step I minus 1. Because if I have even one blue vertex, case 1 has already solved it. Okay. So this is the first claim that I make. I claim that there is a player 2 vertex U that has another edge, that has an edge to another vertex V in this trap. Okay. And I don't know which player V belongs to, I don't care. But my claim is that there is a player 2 vertex U that has an edge to another vertex in the trap. And this edge was not there in GI minus 1. This is a new edge that is only added in GI. Can you prove this? So answer this why. It's actually very intuitive when I tell you, so you will be embarrassed for not finding this out immediately. Okay. Do you agree that there should be some edge here that wasn't in GI minus 1? Because if all the edges that are in SI here were also here, then I would have the same trap SI on the left side too. And I would find it there. So there is at least some new edge here. But what I'm claiming is that there is a new edge that is coming out of a player 2 vertex. But why is that? Well, let's use our assumption. All of the player 1 vertices were white in this side, in GI minus 1. If they were white, it means that the number of edges that they had the number of outgoing edges was at most 2 to the power of I minus 1. So all of their outgoing edges were already included in GI minus 1. Because remember, we said if we have a vertex that has at most 2 to the power of I minus 1 outgoing edges, we put that vertex and all of its edges in GI minus 1. So I cannot have a new edge that comes out of a player 1 vertex, because if I had something like that, that player 1 vertex would be blue, and I don't have a blue vertex. So the new edge has to come out of a player 2 vertex. That's it. So this proves that there is a player 2 vertex U that has an edge to another vertex V, and these are both in my trap in GI, but this edge did not exist in GI minus 1. Okay, now finally I'm going to use the ordering on my edges. Hopefully you remember that I had an ordering on my edges. Okay. What do I know? Let's go back here to the definition here. So for every vertex, I'm putting the first 2 to the power of I in edges, the first 2 to the power of I edges that are coming in. Okay. So, but this is a new edge. This is an edge that didn't exist before. But even in this graph, I had the first 2 to the power of I minus 1 edges that were coming into V. Right? So what this tells me is that this edge was not one of the first 2 to the power of I minus 1 edges that come into V. Okay. But then what else do I know? So let's take a look at V, and let's take a look at all the edges that were coming into V. And one of them is the edge UV. There might be more edges, and there are some edges that came before this. Okay. But what do I know about vertex U? which player does it belong to? It's a player 2 vertex. Is U a target vertex? No, because it's in my trap. I'm not including target vertices in my trap. That would be stupid. Okay. But here, you finally understand why I had this ordering here. I said that I order the edges such that I put the edges that are coming out of a player 2 non-target vertex first. Right? So this edge, this new edge from U to V, it's actually a high priority edge. It's one of those edges that was numbered first. So it means that all the edges that were before this, these were also high priority edges, because otherwise this one would get a smaller number. So this means that all of these previous vertices, let's call them W1, W2, and so on, that had edges to V, and these edges were included in GI minus 1, all of these were also player 2 vertices, and they were not target vertices. Okay. What does that tell you? I have this vertex V. V is inside my trap. I have a bunch of player 2 non-target vertices that have edges to V. What does that mean? It means all of them are in the trap. Well, I mean, we found the trap using our reachability algorithm, so we always find the largest trap in the current subgraph. So yes, they're already in this trap. So all of these vertices are inside my trap. But how many of them do I have? I have at least 2 to the power of I minus 1. Right? Because these are the vertices that had edges to V in GI minus 1. But by my second rule here, for every V, I added 2 to the power of I minus 1 in edges in GI minus 1. So I have at least 2 to the power of I minus 1 W's here. And all of them are inside this trap. So the size of my trap is at least 2 to the power of I minus 1. And this finally ends my proof. So I spent a time that was O(n) times 2 to the power of I. And I found a trap whose size is at least 2 to the power of I minus 1. And this was proof by 2 cases, casework. I know this was really complicated, but it works out. So here's our summary. It took us 2 to the power of I times n time to find the trap that has a size of at least 2 to the power of I minus 1. So let's call the size of this trap K. So in order to find the trap of size K, I'm spending O(n)K because this is at most twice K. Right? So finally, I just remember that here in my algorithm, I said that instead of VJ, I can put any trap. So I do this. I say, let's have the same algorithm that we had for Büchi, but every time just find the trap of size K that was computed using this hierarchical decomposition algorithm, take its attractor, add the attractor to the winning set of player 2, and just continue like that. Now, each iteration takes O(n)K time and adds at least K vertices to W2. So my total runtime is O(n) times the sum of all these Ks. But K, the sum of all these Ks is at most n because W2 can have a size of at most n. So my total runtime is O(n) squared. So finally, we have an algorithm with runtime O(n) squared that solved Büchi. Any questions? At some point, I will ask you to code this algorithm if you don't ask any questions. Okay. So let's go on and let's now talk about something more general. So these were our algorithms for solving Büchi. We first saw a classical algorithm that took nm time, and then we saw another algorithm that took n squared time, asymptotically. But now let's say I want to solve a parity game. can you somehow extend the algorithm that we've seen for Büchi to the case of parity games? Now, one main problem that we have when we get into parity games is that we don't even know if these games are determined. Right? For reachability and for Büchi, we had very simple proofs that showed that the game is determined. We could always find a winning set for player one, and then if we were outside of the winning set of player one, we had a simple strategy for player two to win. And so we saw that those games were actually not only determined, but they were also determined with memoryless strategies. Now, the question here is, if I have a parity game, is it going to be determined? Well, the answer is yes, we're going to prove it. And then, is it determined with memoryless strategies? And again, the answer is yes, and we're going to prove it, but it's not obvious at all. And actually, it turns out that when we prove this, the proof will also give us an algorithm for solving parity games. Okay, so first of all, let's just recall what a parity game was. So it's a zero-sum, and I'm just assuming all of our games are zero-sum. So it's a zero-sum infinite duration graph game. We have a priority function P that is assigning a priority from 0 to D to each one of our vertices. And then the objective of player one is parity of P, which means that player one wants to make sure that in the outcome of the game, if we look at all the vertices that were visited infinitely many times, and if we look at the smallest priority among these vertices, that smallest priority is even. That's what player one wants to ensure. Okay. And again, because we are assuming the game is zero-sum, we've already seen this last time. We've seen that the objective of player two is going to be parity of P plus one, because the dual of parity of P was parity P plus one, for instance. Okay. And also, if we don't have priority 0 at all, we can also say that the objective of player two is parity of P minus one, because you can just shift the priorities forward or backwards, but in order to shift it backwards, you shouldn't have priority 0 in the first place, because you cannot have minus one. Okay. So let's do a bunch of claims and let's prove them. First of all, I'm going to do an induction on the number of priorities on D. Okay. Actually on D plus one, to be more specific, because we have D plus one priorities. So everything that I say from this point until the end of this lecture is inside an induction. Okay, just remember that. Now, here's the first thing that I want to do. I want to say that without loss of generality, I can add two assumptions. First, I can assume that either priority 0 or priority 1 exists in my set of priorities. So there is a vertex that has either priority 0 or priority 1. Why can I assume this? Because imagine that all of my priorities are 2 or larger. I can just shift all the priorities by 2. Right? I just subtract 2 from all the priorities and nothing changes. So I can do this to simplify my problem a little bit. But the second assumption is that I'm going to assume that my priorities are contiguous. So I'm going to assume that if I have 2 priorities somewhere in my graph, I have all the priorities in between as well. Now, why does this work? This is, again, actually the same thing. It sounds different, but it's basically the same. So let's say that I have some priority I, and I don't have priority I plus 1. And let's say I have priority I plus 2. Now, what I can do in this case is that I can merge I and I plus 2. Anywhere that I have I plus 2, I can just put I. And nothing changes. Again, in the game, like an outcome would be winning for player 1. If would be in the objective of player 1, if and only if it is after this change. Now, what if I have I don't have I plus 1, I don't have I plus 2, I have I plus 3. Well, I can take priorities I plus 3 and higher, and I can shift all of them to the left by 2 positions. So I take I plus 3, I turn it into I plus 1. I plus 4 becomes I plus 2, and so on. So I just subtract 2 from every priority that is at least I plus 3. And again, nothing changes in my game. So, but what happened here is that I could create priority I plus 1. So I could make sure that all of my priorities are contiguous. Okay. So from now on, I'm going to assume these things. I don't know why I can't delete this now. I'm going to assume my priorities are contiguous, and I'm going to assume that I'm doing an induction. So I have to do the base case of the induction, right? So what is the base case of the induction? What if I have only one priority? If I have only one priority, that priority is either 0 or 1. If it's 0, if everything has priority 0, then player 1 is going to win no matter what, right? Every outcome is good for player 1. If the only priority that exists in the game is 1, then player 2 is going to win no matter what. So in any case, the important point is that the game is determined and they have memoryless strategies. And what is the memoryless strategy that works? Just any strategy, because the strategy doesn't matter at all. Okay. Now, the second base case is if we have 2 priorities. So if I have 2 priorities, my priorities are what? Given that I had this simplification without loss of generality here, if I have only 2 priorities, they are either 0, 1 or 1, 2, right? Those are the only cases. But if I have priorities 0 and 1, what kind of game do I have? So remember when we were proving that Büchi is a special case of parity, we said that if you just take parity with priorities 0 and 1, that's Büchi. And if you take parity with priorities 1 and 2, that's ko-Büchi. And we've already proven that both of those types of games are determined and they have memoryless strategies. So if I have 2 priorities, then again, the base case of my induction holds. I'm either in a Büchi game or in a ko-Büchi game. And I have memoryless strategies and I have determinacy. Okay. Now finally I can do induction. And now I say that I want to prove it for D, and I can assume it for all the smaller values. So for D minus 1, D minus 2, and so on, I can assume that I've proven that the game is determined and has memoryless winning strategies. Okay. So here's another thing that we can do. If we have more than 2 priorities, without loss of generality, we can assume that priority 0 appears in the game. Why can I do this? No, well, let's say priority 0 does not appear in the game. I just subtract all the priorities by 1. And we've seen that that dualizes my game, right? So it's like, look here. Player 1 wins with parity P if and only if player 2 does not win with parity P minus 1, right? So if the objective of player 1 is parity P and I don't have priority 0, then the objective of player 2 is parity P minus 1. So I can just solve parity P minus 1 instead. And parity P minus 1 will have 0 in it. Okay. So without loss of generality, I can assume that I have priority 0 as well. So let's say my priorities are 0 to D, and I have D plus 1 priorities. So based on all these without loss of generalities that I've said until this point, I have all the priorities from 0 to D. Okay. What else do I know? So I have D plus 1 priorities. And because I'm doing induction, I know that I can assume that any parity game with D priorities is memoryless determined. Okay, so basically I have D plus 1 priorities. I have to get rid of one of them. And the easiest one to get rid of is 0. So I want to get rid of priority 0 somehow in my game. Okay. So we want to somehow get rid of all vertices of priority 0 and find a subgame. Now, this is again the definition of subgame, but You remember it, hopefully. So it's just that I'm taking some subset W of my vertices, and I can define a subgame as long as I can make sure that every vertex in W has a successor in W itself. Okay. And this was what we used for our previous algorithms for Büchi as well. Okay. Here's what I'm going to do. I'm going to basically apply something very similar to my Büchi algorithm, except that I'm going to say my target set is my set P0, the set of all vertices that have priority 0. Okay. So let's say P0 is the set of all vertices that have priority 0. And then I compute A and B just the same way that I did for Büchi. So I'm going to say that A is the attractor 1 of P0. So from every vertex in A, player 1 has a memoryless strategy that can ensure we will eventually get to P0. And B is the complement of A. So B is a trap. And for every vertex in B, player 2 has a memoryless strategy that makes sure we will remain in B. And no matter what player 1 does, we can never go to the left side to A. Okay. So B traps player 1 outside of P0. Actually, it also traps player 1 outside of A. Okay. We can define a subgame on B. Why can we define a subgame on B? Because B is a trap. That's like the one lemma that we keep using. If you have a trap, you can define a subgame on it. Okay. Now, the good point here is that all of my priority 0 vertices were in P0. So they were in A. So if I define a subgame on B, that subgame is not going to have any priority 0 vertices, which is awesome because that's all I wanted. I wanted to have one fewer priority. I can say that the subgraph, the subgame on B has at most D priorities. So I can use the induction hypothesis and I can say that the subgame on B is determined with memoryless strategies. Okay. So yeah. But if the subgraph on B is determined with memoryless strategies, it means that I can divide it in two parts. The vertices where player 1 has a winning strategy and the vertices where player 2 has a winning strategy. That's the definition of determinacy. So I do that. So I say let B1 be the winning set of player 1 in the subgame on B. And let's say that B2 is the winning set of player 2. Okay. These are not winning sets in the original game. They're just winning sets in this subgame, on the subgame on B. Okay. So here are my claims. My first claim is that player 2 has a winning strategy, not only in the subgame, but also in the original game, if the game starts somewhere in B2. Can you prove this? So I know that in the subgame, if I don't have A and the game starts somewhere in B2, player 2 wins. Player 2 has a winning strategy. And that winning strategy is also memoryless. I know all of this by induction hypothesis. But I'm saying consider the original game, which also has the A part, and let's say that it starts here. Let's say it starts in one of the vertices of B2. I claim that player 2 can win in this case as well. Prove this claim.
Well, you can never go to B1 because otherwise the other player will win. And the other cases, if you go to AN, but that's where they have strategy to go because it's easier and similar.
No, well, you can't really say that because you see, you're now saying that player 2 should avoid A and B1, and he should also win in B2. But he does have a strategy to win in B2. How do you know that this strategy doesn't get us into A? That's the problem. Like, you have a strategy for winning in the subgame, and you also have a strategy for avoiding A. But you have to somehow show that these two strategies coincide, because you cannot play two strategies at the same time. Okay, but this is actually easier to reason about if you just look at the fact that B is a trap. Since B is a trap, player 1 can never get into A. Right? That's the definition of a trap. There is no edge that takes player 1 from a player 1 vertex in B to some vertex in A. Okay, so if I start here, I'm just going to play the same strategy as player 2. I'm going to play the exact same strategy that I was playing in the subgame. And I'm sure that I will never leave the subgame because the subgame was inside the trap and player 1 cannot leave this trap to go back to it. And I know that I won in this subgame, so I would win overall. Does that make sense to everyone? So basically, because B is a trap, player 1 can never go out of B. And then player 2 had a strategy to win in B. And that strategy never went outside of B either because it was in the subgame B. So if player 2 just plays the exact same strategy, the game will never leave B. And so basically we're playing the subgame in the original game. So player 2 has a winning strategy from every vertex in B2 in the original game. And this is exactly the same strategy that he would play in the subgame. Okay, nice. Here's my second claim. So we're doing this double attractor strategy that we had in Büchi again. So I'm saying, forget about the subgame and whatever. Now what do I know? In my original game, I know that if the game starts in B2, player 2 is going to win. So let's take the attractor of B2 and let's call that C. And this is going to be attractor 2 of B2. So C is the set of all vertices from which player 2 can force the game to reach B2. Okay. I'm claiming that every vertex in C is also a winning vertex for player 2. Why is that? So you see, I've already proven that if the game is in B2, player 2 wins. But I'm saying, consider a vertex from which player 2 can force the game to reach B2. If I force the game to reach B2, can I then win the game? Well, you have to talk about the fact that parity objectives are tail properties or tail objectives, as we talked about, I think, on Tuesday, right? So if I have some outcome of the game, and if I chop off some finite prefix, it doesn't change anything. It doesn't change the set of vertices that are seen infinitely many times. So it doesn't change the overall parity. It doesn't change who wins the game. So in this case, if I start somewhere here, then player 2 can make sure that after a finite number of steps, I'm going to reach B2. But those finite number of steps, they don't matter. No matter what kind of priorities they saw a finite number of things. And we don't care because we only care about things that we see infinitely many times. We only care about vertices that are seen infinitely many times. So as soon as I reach B2, then I'm going to win again as player 2. So yes, we proved this one as well. And also the winning strategies that I used for both of these claims are memoryless. Now, why is that? In the first claim, I just said, use the exact same strategy that you were using in the subgame. And the subgame was my induction hypothesis. And so it's memoryless. I can just assume that. Now, in this second case, I have, what is my strategy? My strategy is that if you're already in B2, play the memoryless strategy from induction hypothesis. If you're outside of B2 but in C, play the reachability strategy until you reach B2. So you just play the reachability strategy, and well, the reachability strategy was also memoryless. So at no point do you need to think about the history of the game. Everything is memoryless. So this is also proven now. Great. Now we're going to do exactly what we did for Büchi. So now I have this set C, and I know that inside of C, if the game starts in C, player 2 will win. What do I do with the rest of the graph? I say it's just a subgame. So solve it recursively. Okay. So, but is this true? Can I have a subgame on V minus C? So if I take the other vertices, the vertices that are not in C, do they define a subgame? Yes, because C is again an attractor. Of course, it's an attractor for player 2, but that doesn't matter. And the complement of every attractor we've seen is a trap. So V minus C is a trap. And we've seen that we can define subgames on traps. So I do have a valid subgame on V minus C. Okay. So basically, again, I have the same exact argument that I had for the case of Büchi. I say that if the game starts here, somewhere outside of C, player 1 would never ever transition to C. Because if he chooses to go to C, he's losing. As soon as he goes to C, player 2 will win. So if there is a player 1 edge that goes in here, I can just delete it. That's not going to happen. And if there is a player 2 edge that goes from outside to inside, that's a contradiction, because if there was a player 2 edge, then I had to put this inside C as well, because C was an attractor. So this tells me that I can really play the part of the game that is outside of C. I can play V minus C completely independently and be sure that I would never reach C if I start there. So I know the answer in C, and then I can recursively just do the exact same thing, compute another C in that remainder of the game, and then continue this until I converge, until I cannot find the set C anymore. Okay. But how long would this continue? So I will find, every time I will find a B, I will find B1 and B2 using my induction, and then I will find C, right? But this continues until at some point C is empty. When C is empty, I cannot find any more winning vertices for player 2, right? But when is C empty? In order for C to be empty, B2 should be empty, because C is the attractor of B2. Okay, so this recursive algorithm continues until at some point I get to a case where B2 is empty. And remember, B2 was the part of B where player 2 had a winning strategy. So if B2 is empty, it means that B is basically equal to B1. Okay, so this is the final case that we have to analyze. So I had this set P0. P0 was the set of all vertices that had priority 0. I computed the attractor of P0 for player 1. So that's A. From anywhere in A, I'm sure that player 1 can ensure we reach P0. And then I took its complement. That complement is B. But then when I looked at the subgame on B, I saw that in that subgame, player 1 wins all the time. Okay, that's what it means for B2 to be the empty set. Okay, now here's the claim in this case. I claim that if I have a game like this, player 1 is just going to win from everywhere. Can you prove this? Can you prove that no matter where I start my game, if I have a situation like this, player 1 is going to win? Just give me a strategy for player 1. Well, you can't really say that because, okay, remember B was a trap for player one. So player one, if we started here, player one could not go to A. But it's possible that player two could go to A, right? So let's consider the different cases. First of all, let's say that I'm here, I'm in B. So if I remain in B forever, if I never go back to the A side, I know that player one will win. But the problem is that B was a trap for player one. It wasn't a trap for player two. So player one cannot go from B to A, but player two possibly can go from B to A, right? And player two knows that if he stays in B, he's going to lose because B is equal to B1. Everywhere in B, player one is winning. So of course, at some point, player two has to decide to go to A. But I want to give a strategy, a winning strategy for player one. So let's say you're player one, you're playing here, and you're playing according to your strategy in this subgame, hoping that player two would never go to the other side. But at some point, player two goes to the other side. So what would you do?
Just keep going to P0.
Yes. So here in A, as player one, you have a strategy that ensures you will see P0. So you just apply that strategy. You make sure that if player two goes to the left, we're going to punish him and we're going to see P0. Okay. Now we're going to remain in P0 for a while, and then we're going to exit P0. If we exit P0 and we are again in A, we're going to apply the same strategy. We're going to see P0 again. Okay. But it's possible that from P0, we jump back to B. Now, if this happens, as player one, we're going to just play our strategy in this subgame, right? So the strategy of player one is simple. Whenever I'm on the right-hand side, I'm going to play the same strategy that I had in the subgame. Whenever I'm on the left-hand side, I'm going to make sure I'm visiting P0. Now, player two basically has two choices. Either he jumps to the left-hand side finitely many times or infinitely many times. If we only spend a finite amount of time on the left, then we're spending an infinite amount of time on the right, and on the right, player one wins, right? So if I'm only spending a finite amount of time on the left, it means that after some time I'm always on the right. But parity is a tail objective. I don't care about the finite prefix of what I've seen. So if I'm always on the right, I'm going to win on the right because player one has a winning strategy on the right. Now, the other case is that player two decides I'm going to go to the left side, to the A side, infinitely many times. But that's fine. If he goes to the left side infinitely many times, every time that he goes to the left, we're going to visit P0. Which means that the total parity, like the minimum priority that is visited infinitely many times is 0, because 0 is literally the smallest priority. And then again, player one wins. So the strategy for player one is very simple. On the left-hand side, in A, play the reachability strategy. Just reach P0. Whenever you're in B, play the strategy for the subgame, which had one fewer parity, one fewer priority in its parity function.
I have a question.
Yes.
Doesn't P1 has control to keep if the game goes somewhere in A, he has a control to always keep it in A because A is an attractor.
No, so A is an attractor, but what player one can do is that he can make sure we will visit P0. But then again, we have that pesky special case that's like when you reach P0, that's your target in your attractor. And you don't know, maybe you reach P0 and this is a player two vertex, and maybe it has an edge to B.
Oh,
So player two can decide to go to B.
Okay.
So basically what I'm saying here is that as player one, you should never care about switching between A and B. You just don't switch between A and B, because in A you can win and in B you can win. You just let player two do the switching. And if player 2 switches a finite number of times, you're going to win. If he switches an infinite number of times, you're going to win. You're going to win anyway. Okay. Great. So, but the most important point here, okay, this is exactly what I told you. In B, play as in the subgame. In A, play with the objective of reaching P0. But this is also a memoryless strategy, right? Because if you are in B, you're playing the same strategy that you had from induction hypothesis, which was assumed to be memoryless. And if you're in A, you're playing reachability, which is also which also had memoryless strategies. So it's memoryless as well. So basically, our induction showed that parity games are memoryless and they're determined with memoryless strategies. Because remember, so we were doing this thing and we were saying that as long as I can find a set C, player 2 has a winning strategy in that set C. And as soon as I couldn't find a set C, I could prove that player 1 wins everywhere. Okay, what's the runtime of our algorithm? Well, it is polynomial kind of, but what is the exact runtime? Can you say? Yeah, but this is now kind of more complicated, right? Because it's not just that we are finding this set C every time, but in order to find the set C, we have to solve another parity game with one fewer priority, right? So here's the thing. If I have this, how many iterations should I do for finding different Cs? Well, this is the same analysis that we had in the case of Büchi. So I have to find at most n C sets, right? And in order to find each one of them, I have to solve first a game of parity with one fewer priority, and then I have to compute this attractor C, which is the attractor of P2. So basically, I have this. If I show my time based on the number of vertices, number of edges, and D, which was the number of priorities, then my runtime is at most n times T of n m d minus 1 plus OM. And this OM is for computing the attractor. And the base case is that T of n m2 is just ONM, which is for Büchi. And actually, we could also put n squared here. Okay, solve this. Okay, come on. This should be either 2711 or 3711. This is easy to solve. Right, so my runtime is n to the power of d minus 1 times n. Because I mean, every time you're reducing d by 1 and you're multiplying by n. So of course you're going to get n to the power of d minus 1. Okay. Great. So here's the summary. We defined two-player games on graphs. We saw what objectives are, what zero-sum games are, what winning strategy, winning set, determinacy, and so on means. You guys are going to show that being zero-sum and being determined are not really that related to each other. And we studied some classical algorithms and we found solutions for them. So we found that reachability and safety can be solved in n plus m, or actually just OM, since m is larger than n anyway. For Büchi and co-Büchi, we found the first classical algorithm, which was n times m, and then this new and improved hierarchical decomposition algorithm, which was n squared. And then for parity with d priorities, we saw n to the power of d minus 1 times m. Now the question is, why did we do all of this? What is the use case? What is the motivation? We will see it in the rest of this course. But at this point, we know we can solve these games.